Hey guys, today's topic is wave interactions. So in what shapes do we find waves? Remember we went over this last lecture. It's transverse and longitudinal. So the shape of that for transverse, remember trans means different. You'll see it perpendicular to the direction of motion. Whereas a longitudinal wave has compression, it has refractions that are a little bit elongated, but then it has more refractions and it moves left to right. Okay. So what happens when a wave hits something? We will start with waves in water as they're easy to make and observe. Okay, every process we see with water waves also occurs with sound and light waves. In water waves, crests are also called wave fronts. So the crest member is the highest point and the trough is the lowest point. So plane waves, or the crest of a plane wave, is a straight line. Okay, circular waves are crests of circular waves, which are circles. So here we go. So plane waves move up or move in whatever direction the lines are moving, that's where they move. Circular waves, as you see, are circles. It's for example, if you had an object here and you disturb that, it would send waves, these ripples or waves, circular waves around the water. Same thing with the plane waves. It says if there's an object here and it's sending ripples down, but this ripple is sending it down, in this direction. Wave interactions are when waves interact with an object or another wave. So there's 4 types of interaction. We have reflection, refraction, diffraction, and absorption. Reflection is the bouncing back of a wave. So bounce, if you see the word bounce, you know it's reflect. And notice the angles are very, very perpendicular. They're straight. So this angle of incidence is equal to the angle of reflection. They're equal. And so if you see a ray like this, you know that is reflection. Refraction is a bend. It's a little slight bending. It's not a straight. If it was a reflection, it would have a light like this, perpendicular. But it does not. It's a slight bent. Here again, slight bent of light. And the speed of the wave changes as it moves from a medium of different density and causes the wave to bend. So right now here it would be in air, and then all of a sudden it goes into glass. It changes. So speed is affected by the density of the medium in refraction. Diffraction is also the bending of a wave as a result of interaction between a wave and the edge of an object. So for example, waves bend around a rock in the ocean, or waves bend around your legs. So for example, if you have an object here and you have slit, so if you have a wide gap, there's a small diffraction effect because the waves are still able to move relatively to the same length. As opposed to if you close that narrow, imagine these are your 2 legs and the water still is wanting to go through. The narrow gap will create a large diffraction as it's trying to spread across. Absorption is when the amplitude of a wave gets smaller and smaller as it passes through a material. So, for example, if you wear dark clothing, you might have heard that that absorbs a lot of the light, and that's why you feel more heat. So this is a similar concept here. Interference is an effect of 2 or more waves intersecting. Okay, and there's 2 types. Amplitude changes and speed and frequency do not. So in constructive interference, so the resulting wave gets bigger. So we call this additive. So for example here, they both add up and we have a higher amplitude. But the frequency still stays the same. In destructive interference, the resulting wave gets smaller and we subtract and they cancel each other out. So sometimes we call this cancellation. So for example here, the in-phase wavelength will come together and it will amplify it. We'll have a higher amplification, frequency still is the same. As opposed to if they're out of phase, for example, you see this one's upward, this one's downward, they cancel each other out. So in a standing wave, or when waves have the same frequency and amplitude traveling in opposite directions, it creates a standing wave. So let's see a video of that. The Doppler effect is a change in frequency of a wave for an observer moving relative to its source. So you might have heard this sometimes with the police siren, and as it moves away, it kind of like distorts the sound, and that's because of how the waves, the sound waves are being made. So for example, we have a source at rest here on the left, and then we have an observer at rest on the right. Well, as the siren is going through, it's eliciting this source of sound waves, and you're listening to it too as it's coming towards you. So it has a certain frequency, and we have a frequency that we hear as a person over here too. So let's say that this ambulance is traveling at 340 meters per second. The sound source moving towards the observer is moving towards it. So you start hearing it, and you start hearing it louder, and you hear it well. Okay. So observer hears increased pitch, shorter wavelength. Right? You hear it very well. Now, what happens if it starts to move away? It distorts the sound because now the waves take longer to reach you. So for example, let's see, like right here, the waves start getting from the source, they start going further and further and further, and so by the time you hear it, it sounds different. Right? Observer hears decreased pitch or longer wave.
I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. What So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.
Most scientists believe that our universe is expanding. That belief is based on an interesting property of light waves called the Doppler effect. Here's how it works. All waves travel outward from a source. A stone dropped in a pond, for instance, will produce waves that move out in a circular pattern from the splash. Light works the same way. When a camera flashes, light waves move out from the flash bulb. When the source of a wave is stationary, the waves can be thought to form circles radiating out from the source. But when the source is moving, something very interesting happens. The waves ahead of the moving source are bunched closer together. The waves trailing behind the moving source are spread out.
We hear this effect when a moving car blows its horn as it passes us. We hear a high-pitched sound as the car approaches us because the motion of the car bunches the sound waves closer together. When the car passes us, we hear a distinct drop in pitch because the sound waves are now spread out by the car.
Light waves show a similar shift. If a source of light, like a star or a galaxy, is moving toward us, the light waves are bunched together, and we see the light with a slight bluish tint. If the star or galaxy is moving away from us, the waves are stretched out, and we see a reddish shift in the color. Because all galaxies show a red shift in the color of their light, this is evidence that they're moving away from one another. So the red shift is evidence that our universe is expanding.